This is a presentation to accompany the on-the-job training smart sheet for CE12, risk and uncertainty. This is the outline of the things I'll go over in this presentation. I want to talk about why we need to assess program uncertainty, and then we'll look at some terms that are important to get a clear definition of up front. And then we'll step through the general modeling process and conducting risk analysis, and I'll provide you some additional resources as we conclude. So this is where we are in the cost estimating process when we get to the point where we need to conduct our uncertainty analysis. So we're right here where this red arrow is, and hopefully we have a point estimate or at least our first iteration of one, and now we're ready to conduct an uncertainty analysis on our program. So why do we need to assess program uncertainty? Inherently, our cost estimate is wrong and actually only represents one value within a range of possible values. Your estimate is no doubt comprised or made up of many different assumptions that may or may not come true. So depending on how the program executes, the actual cost will be something different than what the cost estimate reflects. And so it's important that our cost estimates are reasonable and realistic so that we can establish accurate budgets for our programs so that they can execute and be successful. So we need to quantify the uncertainty within the program to obtain that realistic budget position. So let's define some terms before we move any further. We'll start with risk. This is defined as the probability of a loss or injury, so an unfavorable outcome. And we define an opportunity as a favorable event or outcome, and this falls on the opposite end of the spectrum from a risk. And then finally, uncertainty is defined as the indefiniteness about the outcome of a situation. And so uncertainty is the spectrum of both positive and negative outcomes that are possible, or both the opportunity and the risks. So it's important to understand the difference between uncertainty and risk. These terms sometimes get confused. In a situation that includes the possibility of both favorable and unfavorable outcomes, uncertainty captures both the opportunities and the risks. Typically in the cost model, uncertainty is examined for the purpose of estimating the risk or the probability that a specific funding level will be exceeded. We don't typically try to quantify the program's opportunities like we try to do with risk. The risk management guide for DoD acquisition also chooses not to address opportunities, but focuses only on how to identify and assess negative events, since programs typically have difficulty in this area during the acquisition process. So our ultimate goal is to quantify the program's risk of exceeding a given budget. So now that we know what uncertainty is, where does it come from? There's a variety of sources, some of which I've identified here at the top. There's inherent uncertainty in the cost estimate itself. There are uncertainties within the inputs of the estimate, whether that be within the data that makes up the cost estimating relationship, or whether it's in the complexity factors or subject matter expert judgment that you've used when you have built your estimate. There's definitely uncertainty around the planned schedule durations for the program, and there's a wide variety of different technical uncertainties. And hopefully this is something that's well identified and documented in the program's risk management process. There could be uncertainty within the program's requirements or even within the assumptions that define the program itself. So all of these things and more create that uncertain environment in the program office. Okay, so these are the uncertainty modeling steps that we'll take a look at. On the right, we have a graphic that depicts these steps in chronological order with a little bit of detail. We'll start with the point estimate as the anchor of our modeling process, and then we assess the uncertainty associated with our point estimate. examining those different sources of uncertainty that we just discussed on that previous slide. And then we select probability distributions and define their bounds. After that, we'll explore whether or not any of these uncertainties are correlated with one another. We typically use a Monte Carlo simulation to model the impact of those risks on the cost. When that's completed, we want to review the results, and then we'll phase the risk dollars appropriately. And finally, we document and present the results and then recommend a funding level. So the starting place is the point estimate. This represents one possible outcome based upon the assumptions and estimating methodologies that we used to complete it. It needs to be as realistic as possible, and it needs to be based on the documented program. This could come from a program's card or a card-like document, but the idea is that it needs to be as complete and robust as it possibly can, and it needs to reflect most likely assessments throughout. You need to be on the lookout for any type of embedded risk or additional resources that are consciously or subconsciously added to the estimate to deal with some kind of perceived risk within the program. You don't want any of that in the point estimate. So I want to introduce an example program that we'll use throughout this presentation. So we'll follow it along through the steps of addressing uncertainty. This is just a brief definition of the program that I'll let you read here for a few seconds. So here's the WBS and the program's initial point estimate. It's been developed and phased, and it's in constant year dollars. Okay, so we've completed our point estimate, and now we're ready to assess the areas of uncertainty within that point estimate. There are a variety of ways to do this. You could use an objective approach where you look at historical data to help you bound the uncertainty, or you could ask an expert to help you quantify the range of outcomes. But once you've identified the areas of uncertainty, we use probability distributions to define uncertainty in the cost model. There are many different distributions you could choose from. I've highlighted probably the two most common here, the log normal and the triangular distributions. Depending on the program and the operating location where you work, you may receive guidance to use others, but for today, we'll primarily be looking at triangular. Selecting the bounds for the distribution is necessarily subjective, and you need to be considering what makes sense for your program. The goal is to have the bounds anchored in relevant data, whether that's from subject matter experts within your program office or from more concrete data sources. The analysis really hinges on these bounds, so you need to be careful as you define these. And remember here at the bottom, garbage in, garbage out. So the quality of the information that goes into helping you define these bounds is definitely important as we consider this. So in terms of modeling approaches, there's really two main approaches to consider, inputs-based and outputs-based. An inputs-based simulation is where you assess and assign uncertainty at the input level within the estimate. So for example, you may put some bounds around a learning curve percentage or a complexity factor or something like that. Inputs is more detailed and it can be more realistic, but it can also be more difficult to model. An outputs-based simulation is where you assess and assign the uncertainty at the output or at the point estimate WBS total level. Outputs-based is easier to model and explain, but sometimes the uncertainty can be harder to assess at that WBS level. In reality, again, your organization likely has its own preferences or policies about which one to use, so again, you'll need to use that method. I've included the scenario-based method here at the bottom of this slide. This isn't simulation-based. What you're doing here is creating realistic possible scenarios for your program and assessing the impact that they might have on the program and then trying to quantify that impact. So continuing with our AIM-Y example, they're going to use an outputs-based method, only modeling uncertainty at those WBS totals. The experts in the program office think a triangular distribution is best and have provided the distribution bounds in the table below. The point estimate is tied to the most likely value there, and the low bound is 90% of that point estimate value, and the high bound is the point estimate value multiplied by those factors in that column. So once you've defined the distribution parameters, you want to examine whether or not there is correlation between elements. Correlation describes the degree with which two variables move together. So within their uncertainty ranges, as one increases, so does the other. And if you have negative correlation, as one increases, the other would decrease. We typically use something called a correlation matrix to define that correlation relationship between elements in the model. And we'll see an example of that on the next slide. But a perfectly correlated element would have or two perfectly correlated elements would have a one-to-one relationship, and a 0 would indicate no correlation between the elements at all. You can see in the table on the bottom right some general guidelines for correlation factors, but in the absence of good correlation data, a 0.30 value is the recommended default for correlation. So again, continuing with our AIM-Y example, here's the correlation matrix with associated values that they were provided by the program office engineers, hopefully that they put together with the program office engineers. Always perform a sanity check to ensure that the correlation values make sense. For example, in this case, you'd want to ask yourself, is it true that if the seeker work turns out to be more complex, then the GNC and test work may be too? Just to make sure if the relationship makes sense. Okay, so at this point in the process, we have our point estimate, we've chosen our distribution for our uncertain inputs, and we've bounded it, and we've addressed any correlation between the inputs. So now we can get the answer, so to speak. We're ready to run a simulation. There are situations where you may not need to run a simulation, but in this presentation, we will be doing so. So as I just mentioned, you may not always need to run a simulation if you're just trying to get the mean value, but in most cases you will need one. Presenting a cumulative probability distribution, or what we call an S-curve, is required for cost reviews and estimate documentation. So it's good to get in the habit of running a simulation. You'll stay familiar with the software that your organization uses, and you'll be able to respond quicker when you do need to run one. Depending on where you work, what your operating location is, the software that your organization uses for the risk simulation may vary. So you'll require specific training on that software tool and the specific parameters that your location uses. A few examples of these parameters are listed here. You'll always want to start with the same seed value for the random number generator so that you can reproduce the same result. You may use Monte Carlo or Latin hypercube sampling types, and most locations probably have a recommendation on how many iterations or trials to run, or that is sufficient to produce model convergence. So we're going to talk generally about Monte Carlo simulations. This is a technique that uses random sampling of a specified distribution to obtain results. For example, if we're given a fair dice, what's the expected value of a given roll? We know that the answer should be 3.5, but we can prove that either by hand rolling the dice a bunch of times or by using a Monte Carlo simulation to roll the dice a lot more times and a lot more quickly. And so using a simulation, in this case we're using Crystal Ball, we can see that our mean is pretty close to what we expected. It's 3.47. You can see that here in the red box. In this case, we only ran 1,000 trials or samples, so by increasing this, we could definitely get closer to that 3.5 that we would expect to see. So back to aim Y again, we've now run a simulation using the triangular distributions and the parameters that we've looked at so far. And in this first slide, I'm showing you the results before any of those correlation factors were applied. And then here on the next slide, here's the results when we have addressed correlation. So you can see that the mean is the same, looking right here, it's at 1167.1. But you can see that the coefficient of variation has changed. If we look at the coefficient of variation on the previous slide, you can see that it's lower than it is when we have correlation between elements. So I'll jump between these two slides again so you can see what I mean. So correlation increases the variance in the distribution. And then in this picture, all I've done is change the view of the simulation results to show the cumulative probability distribution, or the S-curve. And we've added some marks along the curve to indicate where our point estimate is, the mean, the 65% confidence level, and the 80% confidence level. And you can see those here. This is your point estimate, this is your mean value, your 65, and your 80. And those are indicated here in the boxes. And so the way to read this chart, for example, would be to say that in this case, we are 65% confident that we can execute the program for $1.2 million, or we are 80% confident that we can execute this program for $1.3 million. And that's that risk of exceeding a given funding level thing that we were talking about before. So once the simulation is complete, it's time to analyze the results. You always need to look at the results and ask yourself if they make sense. It may be difficult to verify that it's right, but you can always assess whether it's realistic. If things aren't looking right, you need to always return to your point estimate and work through the modeling steps again to try to identify any errors that may have been made. And then once you're confident in the results, that things make sense and are realistic, you can work different trade space analyses to show what you might be able to do with the quote-unquote risk dollars that resulted from the risk modeling. What you want to do is develop some realistic scenarios that may occur in the program and then explore how those issues can be addressed with the risk money that the program has. So if the point estimate is $10, for instance, and the mean confidence level is $15, that's $5 of risk money that you want to conduct some trade space analysis on. I've listed a few examples here, but essentially what we're trying to do is just use these scenarios to independently validate the results of our risk analysis. We want to run the trade space analysis and then ask ourselves if it makes sense given the program's overall risk posture. So here's an example of a trade space analysis on the non-recurring engineering labor at the peak burn rate in an EMD program. We know we have $101.8 million in risk money, and our peak burn rate is $7.3 million per month. This is given to us at the bottom of the slide. So with a little division, we can calculate that we can extend the program schedule 13.9 months at that peak burn rate. Given our risk assessment for this element, we can then assess whether or not this seems reasonable given the initial program schedule and the program's level of risk. You'll always want to consult with the program team and involve them in the development of these trade space scenarios, and then always get feedback from them once you've done the analysis to get their buy-in that it also makes sense. Okay, now that we have our simulation complete, we believe our results make sense, and we've gone ahead and run some trade space analysis, we need to phase our risk dollars back into the program. There are multiple ways to do this, and some of them may be situation specific. Some of the options you have include carrying those risk dollars above the point estimate, almost like management reserve. You could also spread them evenly based on the point estimate phasing, or you could get more specific and you could spread them based on specific scenarios that might play out in the program. And again, this is not a decision made in a vacuum. You'll always be involving your program team in this. So let's look at a few quick examples to help illustrate the phasing options that we have. And this is just examples of several different types, not all inclusive. In this first one, we're spreading the risk along the point estimate. You might hear this method called peanut butter spreading the risk. Basically, you're just spreading those dollars on the original point estimate percent allocation. This is sometimes kind of the default method. It's pretty easy, but it's not always the best or the most accurate or realistic method. In this example, we're phasing our risk to address technical issues that we anticipate. So technical issues often result in schedule slips or having to add additional manpower to try to recover schedule. So you want to phase that risk at the point in time when those technical issues are believed likely to develop. And finally, a quick example on phasing schedule risk. If there's minimal slack in your program schedule and a high probability of a slip, you may want to put all of the risk money at the end of the program to allow for the schedule to continue after that planned schedule end. And this is what this example shows. You always want to document the estimate well. This is not unique to the risk assessment, but is an important part of the general estimating process. In terms of the risk assessment, though, you specifically want to document the risk assessment process or the ratings that you have concluded, as well as the assumptions used in defining those distributions. This will help you remember what you did, as well as help you prepare to present your results. And you'll typically present the risk analysis results when you present the rest of the estimate. What you present will depend on the purpose of the cost estimate review, but there are some things that are a part of almost every review. Part of this is presenting the uncertainty analysis process and the things that you did as a part of that analysis that are specific to your program. Hopefully the items on this slide are beginning to look familiar to you as you get familiar with the estimating process and presenting results of your cost estimate. So a cost model is a living product. Hopefully the program manager will be working hard to address their risks as the program executes, and you need to be tracking this and working to understand the impact that it has on the estimate. There are a variety of ways that the program manager can address risk. Some of those risk mitigation options are in the second bullet on this slide. But, you know, as they address their risk and handle issues as they might materialize, you just need to be involved in this process and realize that it does have great impact on your estimate. And then finally, the annual estimate update needs to include any risk updates as well, like the ones that we've discussed on the last few slides, as well as any other program changes, of course. This is the time to officially roll all of that into the estimate and present it for approval. Okay, so in closing, here are some additional resources you can access if you'd like to learn more. Specifically, I'd recommend you take a look at the Joint Agency Cost, Schedule, Risk, and Uncertainty Handbook. It's a very detailed document with a lot of helpful information in it.